So we're going to be talking about rotational kinematics this week and in this video. And one of the key pieces to helping make sense out of this whole rotational unit is to learn about analogs. An analog is something that is very, very similar and can almost be used in place of where we can see strong similarities between the two items. An example of an analog is there are species of deer in some parts of the world that filled the same ecological niche as rabbits do in other parts of the world. So in those cases, the deer are the rabbit analog for their ecosystem. In our class, for basically every single linear thing that we've learned this year, there is a rotational version of it, a rotational analog. So for example, and we've talked about some of this already, in linear terms, we have the value x, which is the displacement from the initial position, or your position or your displacement, and we measure it in meters. The rotational analog of displacement is angular displacement, which is we use the Greek letter theta to represent it, and it's measured in radians. The next linear variable that we've learned about is velocity. Velocity is measured in meters per second, and there is a rotational analog that if you take the angular displacement over time, you do theta divided by time, I guess we'll write that in there, theta divided by time, that's equal to omega, which is the angular velocity, or as I will often call it, the velocity. That's not the real name for it. Nobody calls it that except for me that I know of, but it's a funny name, so I call it that. So velocity is the angular version of velocity. If we take velocity and divide it by time, we should know already that we get acceleration, which is meters per second per second. And there is an angular analog for that. Omega divided by t gives us angular acceleration measured in units of radians per second per second. So angular acceleration is the real term, but since alpha, the Greek letter alpha, looks like a fish, a couple years ago, students started calling it fish acceleration, and I've enjoyed that ever since. So this is really angular displacement, angular velocity, and angular acceleration, but don't be surprised if I call it theta, velocity, and fish acceleration. So now that we have those rotational analogs, we're going to look at some of the equations that exist in linear terms, and we'll see what the rotational analog equations are. So the first rotational motion equation that you guys have on your formula sheet is V equals V naught plus AT. The rotational version is just going to replace all of the linear terms with their rotational analogs. Gosh, I've said that word a lot. So V will become omega, V naught will become omega naught, and then A will become fish, and then T stays the same because T is not a linear or rotational, time's just time. For the next equation, x equals x naught plus V naught T plus 1/2 AT squared, there will be a rotational analog. And for our final equation for kinematics, we have V squared equals V naught squared plus 2A times, I'll just write in delta x. I think it's x minus x naught on your formula sheet, but this means the same thing. So if you'd like, pause it right here and try and put in the rotational analogs on your own. I'll wait. Amazing. You guys did a great job. Yes, that is correct. The rotational analog for this would be theta equals theta naught plus omega naught t plus 1/2 fish acceleration times t squared. And then we have, for the next one, velocity squared equals velocity naught squared plus 2 fish acceleration times the delta angular displacement. Okay, so we'll see a lot more of these analogs as we go through here, but I just have an example problem now that I'm going to do, where really what I'm actually going to do is I'm going to cheat a little bit. I'm going to use a technique that I hope you guys use also on the exam. If you come across a rotational motion problem, very often, unless it's asking specifically for a comparison between linear and rotational motion, usually you can just kind of ignore the rotating parts and look at it as just a linear problem. So for example, this problem says a wheel starts at rest, begins to rotate with a constant increasing angular velocity. What could you measure to find the angular, oh, that's not the right word, that should say acceleration. My bad. Let me fix that real fast. Acceleration. Great. So I'm going to get rid of the terms that have to do with rotational stuff. Let's change it from a wheel. Let's just make it an object, like something that's sliding, like we're familiar with. An object starts at rest and begins to, let's just say it moves with a constantly increasing, angular gross, with a constantly increasing velocity. What can you measure to find the, let's just call it angular acceleration. All right, at this point, this is now a very familiar problem that we've done many times and we probably can think our way through. This looks like a kinematics problem. So let's make a list out of our linear kinematic variables. It says that it starts at rest. So we know V naught is 0. It says that it begins to move. We can also assume that its initial position is 0. We just got our object that's moving, so we'll say that its initial velocity is 0, but it's going to have some kind of acceleration in that direction. Let's call this 0. Let's call this direction positive. All right, what equation should we use here? Well, we have V naught and X naught. So we probably want to use one of the equations that has V naught and X naught in it, so we can just cancel them out pretty easily. That means that we're going to use one of those two equations. We're trying to find angular acceleration, so we want something that has A in it. Well, if we used x equals x naught plus v naught t plus 1/2 at squared, and we're asking what we could measure to find the angular acceleration, we already know these two terms, and we said that they were 0. So if we could just measure the time and the final the final displacement, we could figure this out. So we just figured out that all we need is x and t, and all we have to do is translate this back into angular terms and say angular displacement and time, and then that finishes our problem. The other equation we could have used is, of course, this one here. V squared equals V naught squared plus 2a delta x. We already, let's see, we could measure this. We already know that it's 0. So we could just measure that. So converting that in, if we knew omega and we knew delta x, delta theta, we have to put it back into angular terms, then we could answer it another way. However, this way is better. And it's better because measuring final velocities or final angular velocities is very, very challenging. Because usually to find velocity, as we've done in some experiments in class, you have to kind of like find the average or the displacement over time, which gives us an average, not a final value. So measuring the total displacement is pretty easy because we can just like count how many times it goes around, or measure how many times it went around in some way. And measuring time is pretty easy. Final velocity is a little bit harder. So that would be the way that I went. But I want you guys to hold on to, I hope, this idea of like ignoring the scary rotational parts and just focusing on what are relatively simple linear or very familiar problems that we've done before. So thank you for watching. That is the end of this video.